Hi everyone and welcome to the new video. Our world is full of surprises. For example, did you know that the commonly used fluorescent lamps looks white, but actually they have a lot of gaps in its colors? In this video I will combine some programming and some science. I will show how to connect a USB spectrometer in Python and we will make some fun experiments with that. I will also show how you can find the budget spectrometer, and if you are not interested in programming you can jump directly into the experiments part. Without further ado, let's get into it. First I will explain how to get a spectrometer, and as we will see it is not really expensive. As an example, I opened eBay. This video is not sponsored and all these pictures are for educational purposes. And if I search here for spectrometer, we can see a lot of results. Let's start with the lowest prices. The cheapest spectrometer I see here, it is from China. It cost about $95 US. I saw some reviews of it and they are pretty good, but interestingly in these original reviews the price was about $50 US, so maybe the prices are increasing. So this is the lowest price I see on eBay now. This picture is interesting. You can see how the spectrometer actually looks like. Here we can see the optical input, here we can see a grating in the mirror, so inside it is not very complex and you only need to add the camera and you get a spectrometer. And technically you can also do a spectrometer yourself with an old CD and web camera. It will be even cheaper. The whole budget will be about $20 US maybe. In this video I will use this spectrometer. It is ready to use and it has a USB port. Again, this video is not sponsored and I bought it on my own. Interestingly, some prices are crazy. For example, this spectrometer was available for $100 US and this seller is trying to sell it for $237, which is just ridiculous. So you must be careful with the prices and don't just give money to resellers. I can also make search more specific and I can search for the USB spectrometer. This price is also not that high and apparently it is located in the US, so it can be more interesting for the US viewers. This model is interesting, but it is apparently more expensive and it is probably a second-hand product. It is not a new one. Here we can also see an interesting model. It has an optical connector. And we can also see more expensive models. I did not test it. So as we can see, we have a different choice. Your budget may vary from about $20 US to like $1,000 US. For my test I will be using this model. It works well for me and this video is not sponsored. I bought it on my own. So let's get into it. Okay, before we will start coding, let me briefly explain how the app works. I opened this page on GitHub. The first part of the app is UI that we can see on the right. And as we can see, the TK interlibrary is used, which is a good thing because we don't need extra dependencies. The spectrometer itself works as the USB camera, and here is used video capture class. We will see it later. Here we can see the UI creation. It works well. I will keep it as is. Here we can see all controls and labels. And here we can see the update method. It is used to update two images. One image to the right shows the preview. For example, if I point the spectroscope to the object, we can see it. And the bottom image is the spectrum graph itself. It's this one. If we add some light, we can see this data. And the next class is used for video capture. As I mentioned before, the spectroscope works as a video camera, so when you connect to a computer, it's detectable as a video device. And the project is pretty old, the resolution is low and I will improve it. A getFrame method is used to show this preview at the right. Wavelength to RGB method is used to show this colorful preview. This method works well, I can keep it as is. And the getGraph method is actually draws this graph as we saw it at the bottom. And it works this way. First we get a black and white image, and then we get data from the center of the image, and this data is used to draw the graph, as we can see. This method also works good. I will keep it as is. The only thing I will change is the resolution. And actually that is it. The last part is the calibration. The idea of the calibration is simple. This is the raw image we get from the camera, and we need to match these pixel coordinates to this wavelength. And to do this, we need a source that we know. I will be using a fluorescent light bulb for that. I will show how it works. But logically it is easy, just 2 points in the linear function. we have 2 points at the graph and we have 2 known points of the specific wavelengths, and that's actually it. Now we see how the app works, let's improve it. Okay, now we're ready to start with Python. If you are not interested in Python and you are a Windows user, you can use the Termino program. It is freeware and it can work with the spectrometer out of the box. It is easy. But I will show how to use this spectrometer in Python, and for this project I will use this PySpectrometer code. First, as we know, the spectrometer has a camera inside, so this application is just reading the data using OpenCV. So in the system, the spectrometer is visible as a camera, and the first thing I need to do, I need to set my video device. First, let's see how it is implemented. And as we can see, it is easy. In the application class, there is a parameter video source. My first video source, it is a web camera that is connected to my laptop. And the second video source is the spectrometer that I am using. So the first fix is easy. I am just scrolling to the bottom and I will add this parameter video source. As we can see, it is a simple fix and it will allow us to use this spectrometer. Let's run the app and see what we can get. And the first part is done. We can see the spectrum, which is a good improvement. But apparently the calibration is not accurate because it was made for a different model. Let's first see what this app can do. It can show the raw data from the camera. It is show the wavelength. I can adjust the brightness. Apparently now it is too bright. I can just move the spectrometer to a different position. For example, this will be better. And now let's return to the code. The first line of code is a calibration, but we will do it as the last step when everything else is done. As we can see, for user interface, TK inter library is used, which is okay. This library works well. Viewers who wish can adjust this screen size and improve it, but I will keep it as is, it's not critical. Interestingly, the calibration can be used as a command line parameter, so we can use it with different spectrometers, but I am using the only one. The app can also record the snapshots, but the resolution is pretty low and I will improve it. As the first step, I will change JPEG to PNG. It's better for scientific data, we don't have a data loss and the image is a bit more sharp. This is the main part I want to improve. As we can see, the application is reading data with the low resolution. It's only 640 pixels, which is too low. Let's do it right now. In the My Video Capture class, I will add 2 variables. Let's see now if we didn't break anything. And we actually did. As we can see, the app is crashing. Let's see what we can get. Line 449. Oh, as we can see, this intensity variable is used the hard-coded value, so I need to change it to the width. I don't know why there was a margin for 4 pixels. I will keep it as is. In this getGraph method, I will change the width because now we changed the data width. Now let's run the app again. As we can see, the app is not crashing anymore and we are reading the data with the higher resolution. I can also press the snapshot button that gives us a screenshot as we saw in the code. As we can see now, I increased the camera resolution, but this spectrum does not fit anymore. This fix is easy. First I will save this data in a variable and then I will resize it to the real width. And now I will use this new image and that is it. And we can run the app again and see how it looks. And as we can see, it is much better now. We see that our spectrum fits the screen. The calibration is still not correct, but the image looks okay. So this is the second improvement and let's go forward. Now let's improve this method snapshot. I want this method to be able to save raw data. I will get the data frame and I will let the parameter to get the original frame without compression. And if the frame is original, I will just return it as is, so it is easy. As we can see, we have less nested blocks now, and let's go forward. I also want to make another improvement. In my video capture class, the data is obtained from the USB camera, but for the calibration and testing, I want to use mock data. And the fix is easy. I added the method read video frame and I added the method read frame mock. And this method is just reading the PNG file, so I can test it without a real spectrometer. And it can be also interesting for viewers as well who want to test the data. And now instead of video read, I can just use this method. Now let's see how it works. First I run the application, I can get the spectrum, I turn my light on. And now I can press a button snapshot and we will have a snapshot. And now let's see how I can mock the data. In the read video data, I can return these hard-coded frames and I can test the code without having a real device. And now I can run the app again and I can see this mock data. Of course, it's not live anymore, it's not moving. But the good thing is that I can test the data with the real spectra without connecting the spectrometer every time. And now we have the last and the fun part. Let's do the calibration. Okay, at this point I have a fully functional app, but it has a slight problem, it doesn't work correctly. And to do the calibration I need to perform several steps. First I need to have a fluorescent light bulb, because this bulb has this very specific spectrum. As we can see, it has a very distinct shape. I can search in Google and I can find the spectrum of the fluorescent light bulb. For example, I had found this page. And on this page I can see that this peak has a wavelength of 630 nanometers. Technically the calibration is easy. I need to click the point and I can see the coordinates in the pixels. And I need to find the proper wavelength. So here I have two values in pixels and they have a values of 630 nanometers and 405 nanometers. Of course, I don't want to enter these values every time, so I will just update the Python code and let's see how it works. So first I need to find the proper values in Google and it is easy. This is the page I have found and here I can see different spectra, so I can easily use it. First I will change the default values. I have only one spectrometer, so I can just update them here. In the video capture class, I will add the constant screen to video ratio. As we can see, this calibration is used in the getGraph method and the fix is easy. I will use this coefficient and I will have these points corrected. And I will use these points instead of the original points. And I set this ratio as a frame width divided by this canvas width. So technically when I click this window, these values will be used correctly. And now let's see how it works. And now I can open the app again and as we can see everything looks good. Here we can see this peak at 400 nanometers, now it is in the correct place. Also that we can see that the rainbow colors are correct. And the last peak is at 700 nanometers, which is also correct. So the app works, our fix is done. Now we're ready to do some fun tests with that. The first light source I want to show is the fluorescent light bulb. Surprisingly, it's a pretty old technology, and first fluorescent light bulbs appeared in the 40s in the pre-World War II era. This lamp has a gas inside, and during the discharge the ultraviolet light is produced, and then there is a phosphor coating that produces these interesting lines. Interestingly, our eyes see this spectrum as white, but technically it is not white, we have these distinct spectrum lines. There is a parameter called CRI, color rendering index, and for these lamps the CRI is not very good because as we can see there are gaps in colors, so technically some colors will be not very good visible. This lamp is not a terrible source compared for example to sodium lights. Those lamps have a yellow color and almost a monochromatic spectrum. Some of these lights has a CRI of 0, and they were used for places like tunnels or parking lots where the color quality is not really important. As we saw in the coding part, a fluorescent light is also good for calibrating the spectrometer. Its spectrum has a very specific lines, and these lines are well known, we can easily find them in Wikipedia. You can see it now on the screen. So when we know this wavelength, it's very convenient for us to calibrate the spectrometer. We don't need to buy the special calibration source. These compact fluorescent lamps are not used anymore, but standard fluorescent lamps I still see often in the offices, so they are still in use. And now let's compare this spectrum with a modern LED lamp. Compared to the fluorescent lamps, LED lamp is a much newer light source. They appeared in the market in the early 2000s or maybe even later. And as we can see, the spectrum of the LED light is much better, it's more continuous, so we can visually understand why the CRI is better for the LED lamps. There are no gaps in the colors. Of course, there are different LEDs on the market, and if you want a really good quality, you can especially search for high CRI lamps. But anyway, any modern LED lamp will be probably better than the old fluorescent lamp. But it depends on what do you need, of course. For the office use, even fluorescent lamps may be good enough. Especially nowadays, the LED's lifespan is not so good. To reduce the costs, the manufacturers are using the higher current for LEDs. And for example, I bought a pack of LED lamps on Amazon and none of them was working 10,000 hours as promised. So I can easily imagine why fluorescent lamps are still cheaper. Okay, I have several more interesting samples to share, but this video already becomes too long and these samples are not directly relevant to Python, so I decided to put these tests in a separate video. I hope that the idea of working with a spectrometer in Python is more or less clear now. Don't forget to press like and subscribe if you want to see a new video with the tests. If you want to test the Python code in more details, a source is available on my Patreon page. I also added some sample files, so you can do the tests even without a real spectrometer. Soon I will publish a separate video with more spectrometer tests and samples. Thanks for watching and see you next time!